Welcome back, everyone. Here we are, still in section 5.1, the chapter about discrete probability distributions and discrete random variables. In this case, we're now looking at an application which is called the expected value in a game. Now, a game could be anything that you bet money on, either in gambling purposes, or it could be in buying insurance or manufacturer extended warranties, things like that, where you pay a little of extra money and you're gambling in a sense that you will get something out of that. Okay, so the expected value in a game is the same as the mean. The difference here with what we were doing before is we're not going to count something like x equals 0, 1, 2, 3, or 4. We're going to make x equal the amount that you could win or lose if you play a game. So for this first example, so let's just say hypothetically in your stats class one day you learned that there's a 51.8% chance that you will roll at least 1 6 if you roll 4 dice. So if you want to calculate that, you can. It would be 1 minus 5 6 to the 4th power, and you'll see that that's approximately 52% chance. So you're going to bet your friends $5 that you will roll at least 1 6 when you roll 4 dice. Just seems like you're going to make this bet and you're probably going to win some money because you correctly realized that the probability that you win is slightly higher than the probability that you will lose. So you have an advantage. So that's good thinking, as I said there. So this table right here summarizes what's going to happen. You could win $5 if you happen to roll that 6. If you don't roll at least 1 6, then you would lose your $5. The probability of winning is 0.518. The probability of losing then would be the complement, 1 minus 0.518, which is 0.482. Okay, so what's the expected value of this game? Well, to find the expected value, that is the mean. Okay, so to find the mean, we have to make this green column x times p of x and fill it in. We multiply each possible x times its probability, put it in this column. So 5 times 0.518 is 2.59. And negative 5 times 0.482 is negative 2.41. And then you add them up, and it turns out it's just 0.18. So the mean is only 18 cents. That's not a lot, but what does it mean? Well, it means that we expect to make about 18 cents for each wager that you make. So if you bet a lot of people, you'll make about 18 cents per bet. So that's actually a pretty good deal, and that's the way casinos work. So for part B, if you make this bet 100 times, how much would you expect to win? Well, you're often going to win. You're going to lose a little bit less often than you win, but you're going to still lose a lot, 48% of the time. So you're only going to make about the expected value, which is 0.18, 18 cents, times 100 bets would be $18. So you're going to come up about $18 ahead. It's important to notice, though, that you can never actually win 18 cents, right? You either win $5 or you lose $5. The average is just what you expect to get. The expected value is what you expect to get on average. All right, so we could have done this with StatCrunch, but since there was only 2 options, it was actually very simple to just go through and do the computations right away. Okay, the second example has to do with a lottery that they have in Arizona where you have to pick 3 numbers, and those 3 numbers have to be all 3 numbers in a row. So if you pick those correct 3 numbers, you win $500, and if you don't, you lose your $1. So if we want to find the expected value for this game, the probability that you pick the 3 numbers correctly, they can be repeated, so it's 1/10 times 1/10 times 1/10 using the multiplication rule, which is 1 in 1,000 or 0.001. So here in the probability for the win or lose, you could win. Well, you would win 500, but you spent $1 for the ticket, so you really have won $499. And the probability of winning that $499 is 0.001 right there. The other option is you lose. You lose your dollar, -1, that's why it's negative. And the probability of that is, again, the complement. So 1 minus 0.001 is 0.999. Okay, so again, this is small enough of a table we can actually just calculate it. You could do this in one line and get -50 cents, or if you'd like to see the table, Do the x times p of x column, multiply 499 times 0.001, it's 0.499, and negative 1 times 0.999 is negative 0.9999, and so you add them together and you get negative 50 cents. So in the long run, you should expect to lose 50 cents per game. Notice that you can never, again, you can't play the lottery and actually lose 50 cents. You either win $499 or you lose $1. But if you play it many times, on average, you're going to lose 50 cents per time you play. So basically half of your money. Okay. In probabilities and interpretations of rare events. Basically, this section comes down to what we'll be looking at in the end of our book about inferential statistics. And we want to know when do we think something seems unusual or rare so that we can, question what somebody says, a possible claim. So this flowchart talks about somebody makes a claim about a population, and then we collect the sample data from that population to see if that seems reasonable. If it does seem to be reasonable, then that's usual and we don't reject their claim. However, if the data seems really at odds with the claim, in other words, the data would be very unusual to obtain, then we say, yeah, maybe that claim isn't right. And then we go back and we do further study. So the rare event rule for inferential statistics essentially says that if something has less than a 5% chance of happening, that would be considered rare, and so we would consider that to be an unusual event. Okay, so these two blue boxes here just tell you give you that information, that if something has less than a 5% chance, it's either unusually high or it's unusually low. So as an example, is the event unusual? So this is back to that 2010 US Census data, same table we've had before. And so is it unusual for a household to have 6 or more people in the family? Well, 6 or more, the chance would be, here's 6, 2.4%. 7 or more is 1.5%. We have to combine these. The or means we have to add. So to determine this, we use the addition rule to combine the categories x is greater than or equal to 6, which is x equals 6, plus x equals 7. And that's 3.9%. So the probability that there are 6 or more individuals in a U.S. household is 0.039, 3.9%, and that is less than a 5% chance, so we would conclude that it is unusual for a U.S. household to have 6 or more individuals. It doesn't seem like that many to me, but apparently, at least in 2010, that was fairly unusual. Okay, parts B and part C are similar. Part C in particular says, is it unusual for a household to have fewer than 4 people in the family? And if you do fewer than 4 people, x is less than 4 is what fewer means. That's the same as x equals anything that's less than or equal to 3. So 0, 1, 2, or 3. So we add up x equals 1, x equals 2, and x equals 3, and we get 76%. So that's way more than 5%, so that would not be an unusual size for a U.S. household. Okay, that's the end of the video lessons for section 5.1. I hope that this has been helpful. Look for other videos that go over the handouts that we normally do in class. All right, thanks. Stay safe. Bye.